A century ago, Albert Einstein revolutionized our understanding of space, time, energy, and matter. We are still finding exciting confirmations of his predictions, like the gravitational waves observed last year by the LIGO experiment. When I think of the theme of today's event, ingenuity, Einstein springs to mind. Where did his ingenious ideas come from? A blend of qualities, perhaps, intuition, originality, brilliance. Einstein had the ability to look beyond the surface, to reveal the underlying structure. He was undaunted by common sense, the idea that things must be the way they seemed. He had the courage to pursue ideas that seemed absurd to others, and this set him free to be ingenious. A genius of his time, and every other. A key element for Einstein was imagination. Many of his discoveries came from his ability to reimagine the universe through thought experiments. At the age of 16, when he visualized riding on a beam of light, he realized that from this vantage, light would appear as a frozen wave. That image ultimately led to the theory of special relativity. 100 years later, physicists know far more about the universe than Einstein did. Now we have greater tools for discovery, such as particle accelerators, supercomputers, space telescopes, and experiments such as LIGO. Yet imagination remains our most powerful attribute. With it, we can roam anywhere in space and time. We can witness nature's most exotic phenomena, while driving in a car, snoozing in bed, or pretending to listen to someone boring at a party. Much of my own life has been spent exploring the nature of black holes, their geometry, evolution, and the fate of those unlucky enough to fall in. These greedy monsters are not easy travel destinations, but they fascinate me, and I keep going back. This year, Andy Strominger, Malcolm Perry, and I have reimagined black holes, examining the energy states of their vacuums, and the information stored on their boundaries, with potentially deep implications for physics. So if our minds, helped by data from telescopes and experiments, can cross the universe, making discoveries along the way, why go anywhere for real? Shouldn't we be content to be cosmic couch potatoes, enjoying the universe from the comfort of our home planet? No, we should not. For two reasons. The first is that the universe is a violent place. Stars engulf planets. Supernovas fire lethal rays across space. Asteroids hurtle around at hundreds of miles a second. Granted, these phenomena do not make space sound very inviting. Yet these are reasons why we should venture out into space instead of staying put. Because if we wait long enough, they will reach us here. I am not doomsaying. It is guaranteed by the laws of physics and probability. Furthermore, we know there is at least one advanced civilization with a propensity for destroying species, ecosystems, atmospheres, and weather patterns, perhaps entire planets. And it happens to live on Earth. Spreading out may be the only thing that saves us from ourselves. The second reason is that we are, by nature, explorers. The same curiosity that sends us to the stars, at the speed of thought, urges us to go there in reality. And whenever we make a great new leap, like the moon landings, we elevate humanity, bring people and nations together, usher in new discoveries, and new technologies. So far, such journeys have been limited to our local cosmic neighborhood. 40 years on, our most intrepid explorer, Voyager, has just made it to interstellar space. But that is still a very long way from reaching the stars. At Voyager speed, 11 miles a second, it would take about 70,000 years to reach our nearest star system, Alpha Centauri. It is 4.37 light years away, 25 trillion miles. If beings on Alpha Centauri are receiving television transmissions from Earth, they are still blissfully ignorant of the rise of Donald Trump. In fact, the distance to Alpha Centauri is so great that to reach it in a human lifetime, a spacecraft would have to carry fuel with roughly the mass of all the stars in the galaxy. In other words, with current technology, interstellar travel is utterly impractical. But we have a chance to change that, thanks to imagination and ingenuity. Last month I joined Yuri Milner to launch Breakthrough Starshot, a long-term research and development program aimed at making interstellar travel a reality. If we succeed, we will send a probe to Alpha Centauri within the lifetime of some of you watching today. Breakthrough Starshot brings together three concepts: miniaturized spacecraft, light propulsion, and phase-locked lasers. A starship, a fully functional space probe reduced to a few centimeters in size and grams in mass, will be attached to a lightsail. Made from metamaterials, the lightsail weighs no more than a few grams. The starship and lightsail, together known as a nanocraft, will be placed in orbit. Meanwhile, on the ground, an array of lasers at the kilometer scale will combine into a single very powerful light beam. The beam is fired through the atmosphere, striking the sail in space with tens of gigawatts of power. The idea is that the nanocraft rides, like Einstein, on the light beam. Not quite to the speed of light, but to a fifth of it, or 100 million miles an hour. Such a system could reach Mars in an hour, reach Pluto in days, pass Voyager in under a week, and reach Alpha Centauri in just over 20 years. Once there, it could image any planets discovered in the system, test for magnetic fields and organic molecules, and send the data back to Earth in another laser beam. This tiny signal would be received by the same array of dishes that was used to transmit the launch beam. This would not be human interstellar travel. Even if it could be scaled up to a crewed vessel, it would be unable to stop. But it would be the moment when human culture goes interstellar, when we finally reach out into the galaxy. And if it should send back images of a habitable planet orbiting our closest neighbor, it could be of immense importance to the destiny of our civilization. Of course, there are major challenges to overcome. How to combine hundreds of lasers through the motion of the atmosphere. How to propel the sail without incinerating it, and aim it in precisely the right direction. How to keep the starship functioning for 20 years in the frozen void, and send a signal back across 4 light years with tiny lasers. But these are not limitations set by the laws of physics. They are engineering problems. The word engineer comes from the same root as the word ingenuity. Engineering challenges tend, eventually, to be solved. As it progresses to a mature technology, other highly exciting missions are envisaged. Even with less powerful laser arrays, journey times to other planets, the outer solar system, or interstellar space, could be vastly reduced. If we find a planet in the Alpha Centauri system, its image, captured by a camera traveling at a fifth of light speed, will be slightly distorted due to the effects of special relativity. It would be the first time a spacecraft has flown fast enough to see such effects. In fact, Einstein's theory is central to the whole mission. Without it, we would have neither lasers nor the ability to perform the calculations necessary for guidance, imaging, and data transmission over 25 trillion miles at a fifth of light speed. So there is a direct path between that 16-year-old boy dreaming of riding on a light beam and our dream, which we hope will become a reality, of riding a light beam to the stars. Thank you for listening.